Welcome to the very first episode of our Machine Learning for Absolute Beginners series. If you are curious about how Netflix recommends shows, how self driving cars make decisions, or how AI like ChatGPT works, you are in the right place. In this tutorial, we are starting from zero, no coding experience, no problem. We'll break everything down in the simplest way possible. By the end of this video, you will understand what machine learning actually is, why it is important, and how you can start building smart models step by step. So grab a cup of coffee, open up your laptop, and let's dive into the world of machine learning together. We have broken down this series into 6 modules: Module 1, Module 2, Module 3, Module 4, Module 5, and Module 6. Prerequisites for machine learning. Before diving into what machine learning actually is, we must have a basic understanding of what Python and some of its most popular libraries are, such as NumPy, Pandas, Matplotlib, Skitlearn, SciPy, and TensorFlow, and you must also have an understanding of SQL. You don't need to have a thorough understanding of this, but having a basic understanding would really help because you are going to use this in your machine learning journey frequently. Over here, we have some of the basic tools that we will be frequently using in our machine learning journey. For data manipulation and analysis, we'll be using NumPy and Pandas. For visualization, we'll be using Matplotlib and Seaborn. For machine learning, we'll be using Skitlearn and XGBoost. Some of the advanced fields such as natural language processing, deep learning, and computer vision, and its libraries such as TensorFlow, PyTorch, Hugging Face, OpenCV. These are advanced concepts and you don't need to know about them. We'll be learning about them in the upcoming videos. So let's start with Module 1, Introduction to Machine Learning. Machine learning can be broadly categorized into 3 types: supervised learning, unsupervised learning, and reinforcement learning. There is also a fourth type called semi-supervised learning, which is a combination of both supervised and unsupervised learning, which uses both labeled and unlabeled data for its model output. We'll be learning about this in the later part of the video. Machine learning pipeline. In this, we will be learning about ML workflow, data cleaning, feature scalping, and data preprocessing in Python. Machine learning. Machine learning allows computers to learn and make decisions without being explicitly programmed. It involves feeding data into the algorithm to identify patterns and make predictions on new data. Machine learning is used in various applications, including image and speech recognition, natural language processing, and recommender systems. As you can see in the diagram below, where data is fed into the machine for training the machine, and then a model is being built, and then the outcome is predicted based on the given data. So it is very important to have a clean data for your machine learning model. Why do we need machine learning? Well, there may be many reasons, but some of the most prominent ones are solving complex business problems such as image and speech recognition in healthcare, language translation, and sentiment analysis. Another reason could be handling large volumes of data such as fraud detection in financial transaction, creating personalized feed recommendation, automate repetitive tasks such as email filtering, chatbots, and data processing, personalized user experience such as Netflix and e-commerce recommendation, and self-improvement in performance like voice assistants like Siri and Netflix, search engines, or self-driving cars. Stages of machine learning. A detailed sequential process of machine learning includes some set of steps such as data collection, data pre-processing, choosing the right model, training the model, evaluating the model, hyperparameter tuning and optimization, prediction, and deployment. Supervised machine learning. As you can see the image below, this image explains supervised machine learning using animals as an example. We start with labeled data, images of animals like cows, camels, and elephants, each tagged with their correct name. This data is fed into a machine learning algorithm which learns patterns and features from these labeled examples. During processing, the model understands how an animal looks based on its feature. Once trained, it can take a new image and predict which animal it is by matching patterns. The final output is the correct label like elephant or camel. Supervised learning helps machine learn from examples and make accurate predictions. Let's get to know about supervised machine learning in detail. Supervised machine learning uses labeled dataset to train algorithms to classify data or predict outcomes. As input data is imputed into the model, it weights modify until it fits into the model. This process is known as cross validation, which ensures that the model is not overfitted or underfitted. A fundamental concept in supervised machine learning is learning a class from examples. This involves providing the model with examples where the correct label is known, such as learning to classify images of cats and dogs by being shown labeled examples of both. The model then learns the distinguished feature of each class and applies this knowledge to classify new images. How supervised machine learning works. Supervised learning algorithm consists of input features and corresponding output labels. The process works through training data. The model is provided with a training dataset that includes input data, features, and corresponding output data, labels or target variables. Learning process. The algorithm processes the training data, learning the relationships between the input feature and the output label. This is achieved by adjusting the model's parameters to minimize the difference between its prediction and the actual labels. After training, the model is evaluated using a test dataset to measure its accuracy and performance. Then the model's performance is optimized by adjusting parameters and using techniques like cross-validation to balance bias and variance. This ensures that the model generalizes well to new and unseen data. In summary, supervised machine learning involves training a model on labeled data to learn patterns and relationships, which is then used to make accurate prediction on new data. In the above image, training phase involves feeding the algorithm labeled data where each data point is paired with its correct output. The algorithm learns to identify patterns and relationship between input and output data. Testing phase involves feeding the algorithm new, unseen data and evaluating its ability to predict the correct output based on learned patterns. Types of supervised learning in machine learning. Now, supervised learning can be applied to two main types of problem. Classification, where the output is categorical variable, example spam versus non-spam emails, yes versus no. Regression, where the output is a continuous variable, example predicting house prices, stock prices, etc. While training the model, data is usually split in the ratio of 80-20, 80% as trained data and the rest as testing data. In training data, we feed input as well as output for 80% of data. The model learns from training data only. We use different supervised learning algorithms, which we will discuss in detail in the next session to build our models. Let's first understand the classification and regression data through the table below. Both the above figures have labeled dataset as follows. Figure A. It is a dataset of shopping store that is useful in predicting whether a customer will purchase a particular product under consideration or not based on his or her gender, age and salary. Input, gender, age and salary. Output will be purchased 0 or 1. 1 means yes, the customer will purchase and 0 means that the customer won't purchase. Figure B. It is a meteorological database that serves the purpose of predicting wind speed based on different parameters. Input, dew point, temperature, pressure, relative humidity, wind direction, and the output will be wind speed. Practical examples of supervised learning. Few practical examples of supervised machine learning across various industries are fraud detection in banking, which utilizes supervised learning algorithm on historical transaction data, training models with labeled dataset of legitimate and fraudulent transactions to accurately predict fraud patterns. Parkinson disease prediction. Parkinson disease is a progressive disorder that affects the nervous system and the parts of the body controlled by the nerves. Customer churn prediction uses supervised learning techniques to analyze historical customer data, identify patterns, association with churn rates to predict customer retention effectively. Cancer cell classification implements supervised learning for cancer cell based on their features and identifying them if they are malignant or benign. Stock price prediction applies supervised learning to predict a signal that indicates whether a buying particular stock will be helpful or not. Now, let us look at some of the most commonly used supervised machine learning algorithms. Linear regression. Linear regression is a type of supervised learning regression algorithm that is used to predict a continuous output value. It is one of the simplest and most widely used algorithm in supervised learning. Logistic regression. Logistic regression is a type of supervised learning classification algorithm that is used to predict a binary output variable. Decision tree. Decision tree is a tree-like structure that is used to model decision and their possible consequences. Each internal node in the tree represents a decision, while each leaf node represents a possible outcome. Random forest. Random forests again are made up of multiple decision tree that work together to make prediction. Each tree in the forest is trained on a different subset of input features and data. The final prediction is made by aggregation the prediction of all the trees in the forest. Support vector machine. The SPM algorithm creates a hyperplane to segregate n-dimensional space into classes and identify the correct category of new data points. The extreme case that helps create the hyperplane are called the support vectors, hence the name support vector machine. Gradient boosting. Gradient boosting combines weak learners like decision tree to create a strong model. It iteratively builds new models that correct errors made by previous ones. Naive Bayes algorithm. The naive Bayes algorithm is a supervised machine learning algorithm based on applying Bayes' theorem with the naive assumption that features are independent of each other given the class level. K nearest neighbors. The KNN works by finding K training examples closer to a given input and then predicts the class or value based on the majority class or average class of their neighbors. The performance of KNN can be influenced by the choice of K and the distance metric used to measure proximity. Training a supervised learning model. The goal of supervised learning is to generalize well to unseen data. Training a model for supervised learning involves several crucial steps, each designed to prepare the model to make accurate prediction or decision based on labeled data. Below are the key steps involved in training a model for supervised machine learning. First, data collection and pre-processing. Gather a label dataset consists of input features and target output labels. Clean the data, handle missing values, and scale features are needed to ensure high quality of supervised learning algorithms. Second, splitting the data. Divide the data into training set 80% and the test set should be 20%. Choosing the model. Selecting appropriate algorithm based on the problem type. This step is crucial for effective supervised learning in AI. Training the model. Feed the model input data and output labels, allowing it to learn patterns by adjusting internal parameters. Fifth, evaluating the model. Test the trained model on the unseen test set and assess its performance using various metrics. 6. Hyperparameter tuning. Adjust settings that control the training process. Example, learning rate using techniques like grid search and cross validation. 7. Final model selection and testing. Retain the model on the complete dataset using the best hyperparameter testing its performance on the test set to ensure readiness for deployment. 8. Model deployment. Deploy the validated model to make predictions on new unseen data. By following these steps, supervised learning models can be effectively trained to tackle various tasks, for learning a class, for examples, to making prediction in real-world applications. Learning with examples. Before moving on with examples, let's do a quick revision of what we have learned recently. What is supervised learning? Supervised learning is when we train a machine learning model on labeled data. This means for every input, the output or answer is already known. There are two types. Classification, when the output is a category or label. For example, predicting whether an email is spam or not. Regression, when the output is a continuous value, like predicting the price of house based on its feature. Let's now move into actual example and visualize them. We will also visualize our result using matplotlib so you can clearly see how the model makes prediction. Let's get started. Iris flower classification. The context is the iris flower dataset consists of three species: Setosa, versicolor, and virginica. These species can be distinguished based on their measurements. Now imagine that you have the measurement of iris flowers categorized by their respective species. Your objective is to train a machine learning model that can learn from these measurements and accurately classify the iris flower into their respective species. Classification with iris dataset plus matplotlib, we use a scatter plot to show how our model separate classes using two features. Import matplotlib.pyplot as PLT from sklearn.dataset. Import load iris. We start by importing the dataset from load iris. From sklearn, we extract only the first two features, sepal length and sepal width, so that we can visualize them in 2D. We split our training set into training and test set using the train test split so that the model learns from one part of the data and is evaluated on unseen data. From sklearn.tree import decision tree classifier. This is our model. From sklearn.metrics import accuracy score. Now we'll be loading the data. Iris equals to load iris, x equals to iris.data 2. We only use the first two feature for 2D visualization, y equals to iris.target. Now we'll be splitting the data x train, comma x test, comma y train, comma y test equals to train test split x, comma y test size equals to 0.3. Now we'll be training the data model equals to decision tree classifier model.fit x train, comma y train, y pred equals to model.predict x test. We then train a simple decision tree classifier, a model that splits data based on feature values and predict which class the flower belongs to. For accuracy, we will be writing the code print classification accuracy score y test, comma y predict. For visualization, we will be using plt.figure figure size equals to 8,6 for I level in Illuminator iris.target names plt.scatter x y equals to I 0 and x y equals to I 1 level equals to level. To visualize this, we use the matplotlib. We create a scatter plot where each point presents a flower and the color indicates the species. We will see clear clusters forming for each flower type, which is what the model uses to classify new flowers. The more separate these clusters are, the better our model is. plt.xlabel sepal length, plt.ylabel sepal width, plt.title iris flower classification, plt.legend, plt.grid true, and plt.show. Now let us run this model. We'll be selecting the python.3 kernel. Let's see. Um, as you can see, we got a classification accuracy of 0.7. It is again loading. Let's see. As you can see, we got a classification accuracy score of 0.5, and you can see the plotted chart over here. As you can see, the classification accuracy is 0.5, which is around 50%. So the accuracy is very low, which is not very good. So we'll be using another model to see if we can increase the accuracy. This is a great example of classification where you can actually see how different classes are separated based on input feature. Let's see for the next model how it performs with the same dataset. Why is accuracy low? Well, there may be multiple reasons. The first one is using only two features. In our current code, we are using x equals to iris data 2. That's only sepal length and sepal width. But the iris dataset has 4 features and the other two, petal size and petal width, are actually more informative. Second, model complexity. Using a decision tree classifier with default setting which might overfit or underfit depending on split and depth. Third, train test split randomness. Train test split by default splits data randomly. That can sometimes create an imbalance or challenging test set. How to fix it? First, use all features. Change this line x equals to iris.data to x equals to iris.data which uses all 4 features. Second, add random state for reproducibility. Add random state equals to 42 to your train test split and model to make it consistent. Third, test a different model or tune hyperparameters. Try models like from sklearn.assemble import random forest classifier model equals to random forest classifier random state equals to 42. Updated version for better accuracy. Random forest classifier. From sklearn.dataset import load iris. From sklearn.model selection import train test split. From sklearn.assemble import random forest classifier. This is our model. From sklearn.metrics import accuracy score. Import matplotlib.pyplot as PLT. Now we will be loading the data as we have done in the previous model. Same, we'll be loading the data, then we will be training the data and then dividing the data into XY split for X train and Y test. Then we will be selecting the model equals to random forest classifier, random state equals to 42, model dot fit X train comma Y train will be predicting Y predict equals to model dot predict X test. For accuracy we will be using print classification accuracy score Y test comma Y predict PLT figure size 8,6 for I, label in Illuminator, iris target name, and for visualization, same code as the above. Now let's run this model of random forest classifier and see what our classification accuracy is. As you can see, we got a classification accuracy of 1 which is around 100%. So this model performs insanely great from the previous model. Regression using California housing dataset. In this example, we use the California housing dataset. It contains various detail about California districts like median income, number of rooms, etc. We will try to predict the median house price based on the median income. Regression with California housing dataset plus matplotlib. Import matplotlib.pyplot as PLT from sklearn.dataset import fetch California housing. We import a dataset and take only one feature, medium income, so we can again visualize it easily in 2D. From sklearn.model selection, import train test split. From sklearn.linear model, import linear regression. This is our model. From sklearn.metrics, import mean square error. Now we'll be loading the data. Data equals to fetch California housing. X equals to data 0. We use only one feature, medic, in for simple 2D plotting. Y equals to data.target. Split will be splitting the data x train x test y test equals to train test split x comma y test size equals to 0.3. Now we'll be training the data model equals to linear regression. We call the model equals to fit x train y predict equals to model dot predict x test. We train a linear regression model which tries to fit best straight line through the data that minimize the prediction error. Print mean square error, y test, y predict. In this, the blue dot represent the actual housing prices and the red dot are predicted prices of our model. If the red and the blue dot are close together, this means our model is predicting well. If there is a large gap, then the model isn't performing great. Then we will be writing the visualization code same as we have seen in the previous models. Plt.figure fit size 8,6, plt.scatter x test y test color equals to blue, label actual, plt.scatter x test y predict color equals to red, label predict alpha equals to zero point 0.6, print x label medium income, y label house pricing, print title regression actual price versus predict price, plt.legend, plt.grid true, plt.show. Now let's run this model. As you can see, we have got a mean square error of 0.68. The less the error will be, the better it is. As you can see the plotted chart over here, regression problems like this are used in real world applications like predicting prices, demand forecasting, or even stock market trends. Unsupervised machine learning. The image below explains unsupervised machine learning. Here we start with raw input data, images of elephants, camels, and crows. But no labels are provided. The system does not know which image is what. The outputs are unknown, and there's no training dataset like in supervised learning. The model begins by interpreting patterns, growing similar data along algorithms and processing techniques. It identifies similarities and forms clusters. For example, grouping all elephants together, camels together, and so on, without being told what each group is. Finally, the output is structured or clustered data, a key feature of unsupervised learning. The image shows set of animals, elephant, camels and cows that represent raw data that the unsupervised learning algorithm will process. The interpretation stage signifies that the algorithm does not have predefined labels or categories for the data. It needs to figure out how to group or organize the data based on inherent patterns. Algorithm represents the core of unsupervised learning process using techniques like clustering, dimensionality reduction, or anomaly detection to identify patterns and structure in the data. Processing stage shows the algorithm working on the data. The output shows the result of unsupervised learning processes. In this case, the algorithm might have grouped the animals into clusters based on their species: elephant, camels, cows. Now, let's understand unsupervised machine learning in detail. Unsupervised learning is a branch of machine learning that deals with unlabeled data. Unlike supervised learning, where the data is labeled with a specific category or outcome, unsupervised learning algorithms are tasked with finding patterns and relationships within the data without any prior knowledge of the data meaning. Unsupervised machine learning algorithms find hidden patterns in data without any human intervention. We don't give output to our model. The training model has only input parameter values and discovers the group or pattern on its own. How does unsupervised learning work? Unsupervised learning works by analyzing unlabeled data to identify patterns and relationships. The data is not labeled with any predefined categories or outcomes, so the algorithm must find these patterns and relationships on its own. This can be a challenging task, but it can also be very rewarding as it can reveal insights into the data that would not be apparent from a labeled dataset. The input to the unsupervised learning model is as follows. Unstructured data may contain noisy, meaningless data, missing values, or unknown data. Unlabeled data. Data only contain a value of input parameter. There is no target value output. It is easy to collect as compared to labeled one in the supervised approach. Unsupervised learning algorithms can be grouped into three parts: clustering, association rule learning, and dimensionality reduction. Clustering algorithms. Clustering in unsupervised machine learning is the process of grouping unlabeled data into clusters based on their similarities. The goal of clustering is to identify patterns and relationships in the data without any prior knowledge of the data meaning. Broadly, this technique is applied to group data based on different patterns, such as similarities or differences. Our machine model finds these algorithms are used to process raw, unclassified data objects into groups. For example, in the above figure, we have not given output parameter values. So this technique will be used to group clients based on the input parameters provided by our data. Association rule learning. Association rule learning is also known as association rule mining is a common technique used to discover association in unsupervised machine learning. This technique is a rule-based ML technique that finds out some very useful relation between parameters of a large data set. This technique is basically used for market-based analysis that helps to better understand the relationship between different products. For example, shopping stores use algorithms based on this technique to find out the relationship between the sale of one product with respect to another sale based on customer behavior. If a customer buys milk, then he may also buy bread, eggs, or butter. Once trained well, such models can be used to increase their sale by planning different offers. Dimensionality reduction. Dimensionality reduction is the process of reducing the number of features in a dataset while preserving as much information as possible. This technique is useful for improving the performance of machine learning algorithms and for data visualization. Imagine a dataset of 100 features about students, height, weight, grades, etc. To focus on key traits, you reduce it to two features, height and grades, making it easier to visualize or analyze the data. Learning with examples. Before diving into the examples, let's first do a quick revision of what we have learned right now. Unsupervised learning is a type of machine learning where the model learns patterns from unlabeled data. Unlike supervised learning, there is no target output or predefined categories. The goal is to explore the data and find hidden structures or patterns. The two most common types of unsupervised learning are: number one, clustering, grouping similar data points together. For example, customer segmentation in marketing using k-means clustering. Second is dimensionality reduction, reducing the number of features while preserving important information. For example, PCA, principal component analysis, used for data visualization or noise reduction. How it works: the algorithm tries to organize data based on similarities and differences. In clustering, it may group points based on distance and density. In dimensionality reduction, it identifies which feature matter most. K-means clustering on synthetic 2D data. One of the most popular techniques in unsupervised learning is K-means clustering, and today we are going to visualize exactly how it works. So let's jump right into the demo. K-means clustering visual demo. To show how this model works, let's create some synthetic data, basically fake data that mimics real-world data clusters. Import matplotlib.pyplot.splt from sklearn datasets. Import makeblobs from sklearn.cluster. Import k-means. Step 1 is to generate sample data. X, y true equals to make blobs, n samples equals to 500, centers equals to 4, cluster standard equals to 2, and random state equals to 42. You can tweak these variables as you need and it will generate a slightly different result. Step 2 is to plot the raw data. Plt.figure, plt size 8,5, plt.scatter x equals 0 and x equals to 1, s equals to 52, plt.title, unlabeled data, input to unsupervised learning. plt.xlabel, feature 1, plt.ylabel, feature 2, plt.grid equals to true, and plt show. Here, each plot is just a pair of numbers. To feature, the color you see here is just for visualization. In a real unsupervised learning task, the algorithm does not see any label. For step 3, apply k-means clustering. K-means equals to k-means n cluster equals to 4, k-means dot fit x, y k-means equals to k-means dot predict. Step 4 is to plot the clustered data using visualization. As you have seen in the previous models, the code is basically the same. plt.figure, figure size equals to 8,5, plt.scatter x0, x1, c equals to y k-means, s equals to 50, and cmap centers equals to k-means dot cluster centers, plt dot scatter title, plt dot y level, plt dot x level, plt dot legend grade equals to true, and plt dot show. Now let's run this model and see what happens. Now we have applied the k-means algorithm. To do that, we'll be grouping this together. Look at that. The algorithm has grouped the data points into four clusters. Each represents a different cluster. The red X mark represent the centroids, the center for each cluster. This is exactly how k-means clustering works. It guesses where the center should be, assigns points to the nearest center, recalculates the centers based on assigned plots, and repeats until the centers stop changing. Let me break down the steps of k-means for you in simple terms. First step is to choose k, number of clusters. Step 2 is to randomly place k centroids in the database space. Step 3 would be to assign each data point to the nearest centroid. Step 4 would be to move the centroids to the average position of the points assigned to them. Step 5 will be to repeat steps 3 and 4 until the centroids do not have any move anymore. This is known as convergence, and once it converges, your data is grouped. Semi-supervised learning. The image below explains semi-supervised learning using vegetables as an example. Here the model receives input data, a mix of tomatoes, carrots, and capsicums. However, only some of the data is labeled, like a few carrots and capsicum, while the rest is unlabeled, such as tomatoes. Using both the partial labels and the unlabeled data, the semi-supervised learning algorithm tries to learn patterns and relationships. Finally, the model makes a prediction on the unlabeled item, correctly identifying the tomato even though it wasn't labeled during training. This approach combines the strength of both supervised and unsupervised learning. Let's understand semi-supervised learning in detail. Semi-supervised learning is an integration of supervised and unsupervised learning. This method uses both labeled and unlabeled data to train the ML models for classification and regression tasks. Semi-supervised learning is the best practice to utilize to solve the problem where a user does not have enough labeled data for supervised learning algorithm. Hence, it is an appropriate method to solve the problem where data is partially labeled and unlabeled. Self-training, code training, and graph-based learning are some of the popular semi-supervised learning methods. Reinforcement machine learning. The image below explains the concept of reinforcement learning. Here, a robot called agent interacts with an environment like a maze. The agent performs an action such as moving in a direction. Based on this action, the environment changes and sends back a new state and a reward, positive or negative, through the interpreter. The agent learns by trial and error, doing action, receiving rewards, and adjusting its strategy to maximize the reward over time. This loop continues until the agent learns the best way to act, like solving the maze efficiently. Let's understand reinforcement machine learning in detail. Reinforcement machine learning is a branch of machine learning that focuses on how agents can learn to make decisions through trial and error to maximize cumulative rewards. RL models allow machines to learn by interacting with an environment and receiving feedback based on their action. This feedback comes in the form of rewards or penalties. Reinforcement learning revolves around the idea that an agent, the learner or decision maker, interacts with an environment to achieve a goal. The agent performs action and receives feedback to optimize his decision making over time. Agent, the decision maker that performs the action. Environment, the world or system in which the agent operates. State, the situation or condition the agent currently in. Action, the possible moves or decision the agent can make. Reward, the feedback or result from the environment based on agent's action. How reinforcement learning works. The RL process involves an agent performing action in an environment, receiving rewards or penalties based on those actions and adjusting its behavior accordingly. These loops helps the agent improve its decision making over time to maximize the cumulative reward. Here's a breakthrough of the RL components. Policy, a strategy that the agent uses to determine the next action based on the current state. Reward function, a function that provides feedback on the action taken, guiding the agent towards its goal. Value function, estimates the future cumulative reward that the agent will receive from a given state. Model of the environment, a representation of the environment that predicts future states and rewards, aiding in planning. Reinforcement learning example: navigating a maze. Imagine a robot navigating a maze to reach a diamond while avoiding fire hazards. The goal is to find the optimal path with the least number of hazards while maximizing the reward. Each time the robot moves correctly, it receives a reward. If the robot takes the wrong path, it loses points. The robot learns by exploring different parts in the maze. By trying various moves, it evaluates the rewards and penalties for each path. Over time, the robot determines the best route for selecting the action that lead to the highest culminative reward. The robot's learning process can be summarized as follows. Number 1. Exploration. The robot starts by exploring all possible paths in the maze, taking the different action at each step. Example: move left, right, up, or down. Second, feedback. After each move, the robot receives feedback from the environment, a positive reward for moving closer to the diamond, a penalty for moving into a fire hazard. Third, adjusting behavior. Based on this feedback, the robot adjusts its behavior to maximize the cumulative reward, favoring paths that avoid hazards and bring it closer to the diamond. 4. Optimal path. Eventually, the robot discovers the optimal path with the least number of hazards and the highest reward by selecting the right action based on past experiences. Cartpole in OpenAI Gym. One of the classic reinforcement learning problem is the cartpole environment in the OpenAI Gym, where the goal is to balance a pole on a cart. The agent can either push the cart left or right to prevent the pole from falling over. State space describes the four key variables: position, velocity, angle, and angular velocity of the cart-pole system. Action space describes action: either move the cart left or right. Reward: the agent earns 1 point for each step the pole remains balanced. Let me show you a real-life working model of this I found on YouTube.
This is our inverted pendulum performing with under control of our PID controller. It is balancing the pendulum in the upright position.
In today's video, we will be building something super cool, a live cardboard reinforcement learning simulation using Pygame for 3D style animation and Matplotlib for live graphics, all powered by a smart PPO agent for stable baseline. The cart problem is a classic control problem in reinforcement learning. We have a cart that can move left or right and a pole attached to the top that needs to stay upright. Our agent will learn to balance it using deep reinforcement learning, and we will display the result in a beautiful animated GUI built with Pygame along with live stats showing the agent's behavior over time. The requirements will be to pip install pygame, pymonk, gym, stable baseline 3, and numpy. We'll train the PPO model first and then load it for simulation. Here is a simple script to train our PPO agent on Cartpole. PPO is one of the most reliable and efficient policy gradient methods available. To do this, import gym from stable baseline 3, import PPO, env equals to gym dot make cartpole v1 model equals to ppo plp policy comma env verbose equals to 1 model dot learn total time steps equals to 20,000 and model dot save equals to ppo cartpole. Once this is done, we'll use the saved model to run the GUI. Now let's dive into the cartpole part, in which we'll be start by initializing the Pygame, setting our screen resolution, and defining the colors for visual. Next step, we map the cardboard position and angle to the screen coordination. This is crucial because GYM gives you values in physics space. We need to convert them into pixels. For real-time stats with Matplotlib, here are the things that gets really interesting. We're embedding Matplotlib live inside the Pygame window using figure canvas AGG. We are plotting only the last 100 steps to keep the things light. For the main loop, we use the trained PPO model to predict the action, step through the environment, collect observation, and then update everything on the screen. This means that the agent is usually controlling the Cartpole in real time and we are rendering it smoothly with visuals and stats. As you can see once we run the model.